and we're going to start talking about HPC tuning and debugging. So until now, if you've taken HPC Intro Essentials, you will know how to run a job on a cluster. But the whole purpose of this course is to basically teach you all the extra skills, the practical skills of what happens when something breaks. How do you see information on what's going on in the cluster? How do you make a better use of the cluster? How do you use it interactively? So that's what this course is about. The actual practice of running on our clusters. Not just running, a first time, a single job, but actually being productive. So obviously our cluster, we're running batch jobs. What are batch jobs? Well, it's basically a program that runs for a certain amount of time. It's a simulation. Let's say you want to run a simulation. Well, that simulation is going to need a certain resources. It's going to need a certain amount of compute time, or a certain amount of time, a certain amount of cores, a certain amount of RAM. So it's compute resources for a certain time, and it's going to run a certain program. And that's basically what a batch job is. And a cluster takes these batch jobs and runs them when there's enough resources available. So usually when you run a cluster, you would submit a job and it may run when there's enough resources. It could be a few days later. But you could think of this as batches of cookies. So a friend offers to bake you some of your famous cookies. Well, what do you need to do? Well, for each cookie type, you need to provide a recipe, which includes ingredients, right? You need a list of ingredients. You also need some information on how hot an oven needs to be, how long it needs to bake, and the actual instructions on what to do. So, here's the analogy to the batch job. Also, depending upon the size of your friend's oven, some cookies are baked at the same time and others are not. When, they're baked at the same time when there's enough room in the oven. If there isn't enough room, then they're left for later baking. So this is the same thing as batch computing. You have a list of resources that you need, how long you need those resources for, and the instructions on how to run your actual program. Okay, so you need a batch script describing the work to be done. That's the recipe. It needs to describe the set of resources required, the wall time, which is the time the job will run. Now, if your job tries to run for longer than the wall time, it will be killed, because you only requested the resources for that period of time. And of course, the actual instructions on what to do. So batch jobs are started by the scheduler when there's enough resources available. Just like you would, your friend would put the batch of cookies in when there's enough room in the oven. So here's how a simple Slurm job script looks like. By the way, Slurm is the scheduler that we are using. And here's how it looks like. You have pound exclamation mark / bin bash. This tells Slurm that we are using bash shell to run this script. And then we have a whole bunch of sbatch. You have the hashtag sbatch, and then information like -- n tasks = 1. What this is in bash, anything after a hashtag is ignored, but Slurm knows that when something begins with hashtag sbatch, it means that it's an option for the scheduler. In this case, it says number of tasks = 1, number of nodes = 1. This job is going to run for 2 minutes. It's going to mail the person who ran this job with it, or at least this email here, when the job starts, when it fails, or when it just ends. It's going to put the output into the specific place. And here we just use a sleep command. And sleep just is a Unix command that, does nothing for that many seconds. And then it goes on to the next command. So sleep basically is just a placeholder here, and we would put in your program that would be doing your simulation right here. So any questions? Okay. So continuing on with our cookie analogy, how to develop a new recipe. Would you use the same process and have your friend bake the cookies? Or would you ask to use your friend's bakery interactively? So if your friend offered to bake the cookies, but would you develop the recipe by having, giving slightly different instructions for your friend, having him bake the cookies, and then coming back to you with the results a few hours, days later? Would you be developing a new cookie recipe like this? Or would you actually be in the kitchen there, checking out what's going on and so on? Obviously, you most likely are going to want to be in the bakery itself, right? Also, if you're trying to make cookie production more efficient, would you ask your friend to fill out some questions and report back to you? Or go into the bakery yourself and observe the process interactively, right? So the idea here is, in both of these cases, you want interactive usage. And the same thing on a cluster. So if you're doing development, you want to work with the job itself, right? You don't want to wait for a job to, you don't want to put together a job, have it wait for a few days to run. And then crash because there is a simple error in your job. That's going to waste a whole bunch of your time. You want to know about the error immediately. By the way, can you guys hear me well? Okay.
Good here, Camille.
Good. Thank you. I got a pop-up which says I'm muted, which I don't know why. But that's good. So we're going to show how to use the Slurm batch cluster interactively. So interactive jobs are used to run a program on a cluster and interact with it while it's running, often for graphical or interactive work, debugging, and profiling. So in debugging, your program may be crashing a lot. You don't want to keep waiting for resources to be given to you. Profiling is watching what's going on with your program. So there's a set of reserved nodes for interactive usage that are set aside for interactive jobs in Compute Canada. But your jobs are not limited to run on these nodes. So if you ask for an interactive job, you can use one of these reserved nodes, but it's not limited to only those reserved nodes. And there's some limitations on these reserved nodes in terms of the size of the job that you may run and how many jobs you have. They're limited to one. These nodes basically are purposely not running no more jobs, and they are just set out for you guys to do development. So interactive jobs have limits, right? To ensure more people get to take advantage of these resources, you're limited to one interactive job per user. There's a limit to the maximum amount of wall time allowed per job, how long we can make this job. And there are limits to the type of jobs that can run. So no interactive job arrays. If the resources to run your interactive job cannot be found in a reasonable amount of time, your request will be canceled. So there's basically two ways of interacting with jobs. You could request an interactive job with the salloc command. So you just do an salloc minus all the regular, like ntask equals 1, everything that you would put in sbatch. And provided that there is an interactive resource available, you would run interactively at that point. So we'll demo this. But there's another way of interacting with a job. Let's say you wanted to run a giant climate simulation. Well, that climate simulation may require hundreds of computers, thousands of cores, right? Well, there isn't going to be that many available, ready interactively for your job immediately. But you could run a regular non-interactive job and then interact with it after the fact, after it starts. The interactive limits don't apply to jobs, as this is a normal job, to these jobs, because this is a normal job. The job, however, this job can't use the resources reserved for interactive usage. And it may take a very long time for it may take a long time for this job to start because it's a regular job, right? But after your job starts, you can interact with it by attaching to an already running job. You just do srun minus job ID equals the job ID, and then minus pty bash. If you have X11, if you have a Unix graphical user interface access, you can do minus X11 as well. Then you can interact with the job with a GUI. But in order for that to happen, you have to be either running from a Linux machine, a Mac, or have X11 installed, an X server installed on your computer in a Windows machine. So you could do that by getting a git bash. And then you would work interactively at this point. Any resource you use will be attributed to your job. So once you attach inside your job, if you start using a lot of resources, then the rest of your job can't use those resources. If your job normally requires 3 gigabytes of RAM, and you've asked for 3 gigabytes of RAM in your job submission, and then you start interacting with it and start using another 2, well, your job will crash because it will run out of memory because it only has access to those 3. So any resources you use, you're going to be inside the job. So you'll be at the limits of what the job can do. So profiling by attaching to an already running job. So one of the things that I like doing is running a script command. So if you run script and a file name, what happens is it will keep whatever the inputs and the outputs of every single thing you type in. So if we do a script test.txt, ls, hello, there's nothing called hello. We type in exit or control D to finish. We will now have a file called test.txt. And in it, you'll see all the stuff that basically we had written in here. The input and the, so you type in something, you could, what's it called, attach to a running job with srun at that point. Also, please remember that you are logged only into one single computer, and your job may span more than others. So it's possible for a single job to run using resources from multiple computers, right? Because one of the flags in the Slurm script is, nodes equals something. So you could say nodes equals 4, processors per node equals 8, and run 32 cores across those nodes. But when you log in, you're actually only logging into a single computer, right? You're not logged into all the computers. Running command printenv, that prints all your environment variables. So all the variables that the Unix shell has. If we could search, so if we search, there's all kinds of environment variables, including ones called user, which is basically your username. So a lot of programs put in options, hide special variables in the shell. And if you print env, you can read all those variables. So this is great for debugging, because if you have a problem in Compute Canada, if you run script and then run printf and all the commands that you're running and how they crashed and so on, well, then it's very easy for the analyst at the end to figure out what happened, because they can see all the environment variables and see what happened. It's also good for profiling, because it keeps a copy of everything that happened. So, interactive jobs for debugging. Run a script to keep a record of any outputs. Run salloc instead of sbatch to launch the interactive job. So if you want to debug something, your program's crashing, but you need to run it on a cluster. So you would run script just to keep a record, run salloc to give you the interactive job. In this case, we'd be asking for 4 tasks with 4,000 megabytes of RAM per CPU. And by default, there's 1 CPU per task. And this would be for 20 minutes in terms of time. We could run print env to print environment inside our job. And we can run top -u user. Top's one of the commands that allows you to, one of the Unix commands that allows you to query what's going on. So, are there any questions? Okay. Now we're going to talk about Unix processes. So if you took the parallelism course on Tuesday, or the session, we talked a little bit more about this, but Unix processes are basically what we would consider programs. Running, each process has a PID, a process ID, which is a unique number. It also has an owner, the user ID, and has a process that started it, and that is its parent, which has its own PID. So often you'll see parent process ID, which is PPID. You could use the PS tree command to show the family of tree of the processes, and they could be killed with the kill command. So let's do that. clear it. So PS3, these are basically processes and the tree of processes that we have here. If we do -u, actually, let's do that. Let's do this first. If we echo $user, that's going to echo your username. So if you do PS3 -u user 13, that's going to show my processes and the tree of my processes. If you are a different user, it will show, well, if you do user 13, it will show mine. If you do yours, it will show yours. But we could just tell the program just to use whatever is in user. In this case, for me, it will be user 13. But for you, it will be whatever your user name is. So here we could see this information. So, okay. PS command shows the processes as well. It can have different options. Each process has a user, a process ID, in this case, how much CPU and memory they use. RSS is actually resident set sizes, how much memory. In this case, when it started, how much time it's been spending in the command that's running. In fact, this PS command sees itself. So when I run this PS command, its process ID was 16,626. So basically all programs have one. Now, programs can use actually multiple threads, multiple cores to run in one process as well, in one program, right? You could think of it like a computer game. You know, one core can be running the AI, another core could be rendering the image, and so on. We're going to use a sleep command. Now, a sleep command, basically, it just sits there for however many seconds, and then it returns. So sleep 3, it's going to be 3 seconds, 1, 2, 3, and it's done. What we can do with programs is we can put them in a background. That command will stay there 20 seconds, and then it will finish. Because we put the ampersand after it, it's in the background. If we type in jobs, we could see that it's running. So the jobs here does not refer to cluster jobs. This is refers to processes. Unix was created piece by piece. So the names were picked piece by piece and not sort of designed in a whole cohesive whole. That's why we have jobs here referring to processes. And here it's actually done. If we do jobs, we can't see it. If we do a sleep, 22 seconds, let's put it. If we want to bring it back into the foreground, we can type in FG, and it's in the foreground. It's back. We're back. If we type in Control C, we kill it. Running the same thing again. If we do foreground, if we type in Control Z, we put it into the background, but we've stopped it as well. It's sleeping. We've stopped the program from running. So if we type in jobs, it's actually stopped. If we, let's run another one as well. So we see we have one running and one stopped. If we would like to keep the program number one and have it actually run again in the background, we can type in BG. And in this case, we're referring to the first program. Oh, and we've restarted, but it's finished. So once again, whenever we have a program that is stopped, we can type in BG. And have it restarted or continued on from where it was. So this way you could pause programs that are running in Unix. One thing that you can do, what happens if you have like sleep of 3,000? Well, that's going to sleep forever, right? And it's running, you want to kill it? Well, there is a command for that. It's called kill. Now we can, so let's create another one. Sleep 2,000. So here we have our two programs. They're going to take forever to run. They both sleep. Right? One is 16,000, process ID, has a process ID 16,879. The other one is right here. Well, we could kill this program two ways. One, we could say kill, and then we could see %, and then whichever one we want. If we want to kill the one that is 2,000, sleep 2,000, the second one, we do a %2. If we want to kill the first program there in the jobs list, we would type in %1. And if we type that, it is being terminated, it is dying.
Okay, Camille, there was a question in the chat about how would you bring a specific background job into the foreground?
Right.
So if you had multiple jobs in the background.
So let's put here we have a few different ones. Let's say we want to bring up the sleep 4,000 job. Well, that is actually the fourth job. So we would do an FG %4. And now it's in the foreground. If we want to put it in the background, Control Z, BG. If there's, I think, one, it automatically starts it running. You may have to do BG and then a %1 if you have multiple things that are sleeping in the background. Or not, yeah, are stopped in the background. So if you run the PS command, you can see that we have multiple things sleeping. Actually, it's a PS UX, I think, yeah. By the way, there's many options you can give to PS or any of our Unix commands. So if you wanted to see which commands and which flags are we using, you would use the man command. And you can look up and down and see what every single flag does. And it'll tell you exactly which outputs and so on. Q to quit, the man page. Anyway, we see here that we have a whole bunch of these sleeps happening. And let's say we want to kill them. We could also kill them by process ID. Oh, actually, no, we don't want to do that. That would kill our SSH session, right? We want to kill the sleep. You don't want to kill your own SSH session. If you do that, it will actually log you off. And it will actually shut down all the programs that are its children. But we'll get to that in a second. Here, we could kill. We've just terminated job %2, but we refer to it by its PID. We can also kill this one here. And I'm going to show you something else. Kill all. It should also work. That one actually kills all the programs that were called sleep, that belong to me. So this way, you can terminate any of the programs that are running. So we have, PS tree. So there's a tree of these processes. Each, so in this case, we have SSH, whose child is bash, whose child is script, whose child is bash, and so on, right? In here, we have SSH, whose child is bash, whose child is PS tree, which is probably the command that I'm running. But there's something that can happen. If you kill the parent, unless you do something very specific, all the children are going to die as well. So basically, when you log in through SSH, right? And then you're running a whole bunch of programs and you log out. Well, SSH is killed, and then all the programs that were running on the computer at the time that are the children of SSH are killed, unless something specific is done. So there's actually a special command. I don't know if I should be teaching you guys this, because if I teach you guys this, well, you will have the power to leave programs running behind. So you need to clean up programs after if you do this. But if you run the command nohup, and then something like sleep 20 or sleep. What will happen is that your program, sleep here in this case, will not be killed, even when your session goes away. So be very careful about this, because you can leave programs running on the login node for months after you leave, because it doesn't die when you log out. On the other hand, it doesn't die when you log out, right? So here we see nohup sleep 2000, which is running. In fact, let's do this. Let's exit here. I've exited here. I have another window open. Oh. Oh. It is still here. There is that sleep 2000 that I started. I've already logged out, but it's still there. So I taught you guys something pretty powerful. Please don't abuse it. But this is the way you can actually keep stuff going after you've logged out. So I have a whole bunch of files here because I've done the previous courses and I've been testing stuff. So I just created a directory and went into it so that there's nothing here. Any questions on processes? I'm putting them foreground, background, killing, and so on. Okay, now I'm going to go here and I'm going to turn on a program called Tmax. The reason I'm going to use this program is because I'm going to want to have two shells open on the same window. I'm going to have basically two terminals so you can see both of them. You could redo the same thing just by having two windows open. So if you can do that. So I'm going to run a program called Tmax. Oh, how do I do this? Yeah, Control B %. Control B. Go. I have two windows now. So Tmax program is pretty cool. It lets you do things like have multiple windows open. It also allows you to have a whole session and then what's it called? Keep it around even when you log out and then come by and reattach to it. But it's a bit more complex, too complex for this course to teach, to use. My colleague Chris is really fond of Tmax. But in here we have two windows. So this way we can see, as you can see, there's a left-hand window and a right-hand window, both in the same tax session here. And we're going to use this for profiling and things like that. Okay, so the next component is profiling our jobs. So let's do that. Well, first of all, let's do the slog. So just an slog by itself. Boom. We've grabbed an interactive node, interactive session. We've started job 76. Notice before we were user 13 on login node 1. Now we're user 13 on node 1, which is actually the compute node. If we do a print env and pipe it to grep, which is a search, and -I for case insensitive, and type in slurm, we can see all the slurm variables. If we did the same thing here, where we're still outside the job, just on a login node, we could see that there's all these slurm variables are not set here when we're on a login node. Here we have the slurm job ID, 76, slurm user ID, user 13, and so on. So by default, if you just do an salloc, you get the default amount of resources. So you get a single core, a small amount of RAM for, I think, half an hour, I think, is default time. But I am inside the job here on node 1. I'm inside job 76. To exit the job, I can type in exit. Now it says as alloc relinquishing job allocation 76. We'll shut down job 76. Right. We should probably go to salloc and give it some more information. I don't know, maybe end tasks equals 2 minus time equals 1 hour 30 minutes. Oh, see, it needs the minus flag. There we go. As we can see here, we're allocated back on node 1. If we type in SQ, okay, let's look at another one now. If we type in SQ, we can see that we have job ID 81, which is actually the one that we are running in. We have user 13, that's me. The job is running. It's running for 1 hour, 29 minutes and 30 seconds that's left. We have one node with 2 CPUs, 256 megabytes of memory on node 1. We see sort of the same thing here, except it's a mess. So in this window here. If we do a print env, grep minus I slurm, pipe to OS minus capital R, we can move up and down. You can see that the job ID, there's an environment variable with the job ID 81, slurm job user is user 13, and so on. Slurm end tasks equals 2, right? Because we've asked for 2 tasks. So we're inside the job right now. So any questions here? Right, so here we are. We've asked for an interactive node, right? Well, what happens if we want to join an already running job? Well, we can do that as well. Here on the right-hand side, we're still in login node 1. But if we run srun minus job ID. And the job ID here is, what is it? It's on the left hand. It's 81. 81 minus pty bash. Now we're on node 1. Okay, there's another way we could check. Well, let's say we want to get the process ID of our shell. There's actually an environment variable for that. It's called echo $. That is the PID, the process ID of our shell. Let's run ps3. ps3 minus u user 13. Oh, it just says bash. But in here, in this example, both the left-hand panel and the right-hand panel now are in the same job. So this is the way you could get into a job that is already running with the srun command. We could do a few other things, but I want to first go through some of the commands that you can use to look at what's going on. So here is a list of some commands. You know, some really cool ones, print env top minus u user. So let's look at that one. Here, we could get back into that same job. Top minus u $user. That shows information on me. So here we can see the process ID, the username, virtual memory, real memory, whether it's running the percent CPU. Maybe we want to go over here. It's 81, right? Job 81. srun minus job ID equals 81 minus pty bash. Let's get into that job. This will be the third session we have in the same job. It's on top minus u user. Here, we can see in a full window a lot more information. We can see the CPU, percent CPU here, percent memory. So top is a command that gives you a lot of information. A lot of the information up here is also on the whole system. So this machine has been up for 10 days since it rebooted. The load on it is actually very small. You can see the total number of tasks and the processes that are running. Most of them are sleeping, so this machine isn't doing very much. We can see how much CPU time, how much CPU there is. We can see its memory, its total memory, its free memory, what's used, what's available, and so on. So top command gives you a lot of information on the Unix system. So in general, these commands that we're going over here, if you want to learn more about them, you could go to the internet and type in Unix commands for, what's it called? System monitoring commands. So there's quite a few of them, and there's different ones that do different things. But the great thing about getting interactive access to the node is that you could use all Unix commands that are out there. So another cue to get out of here, we could run htop minus u user. That's a different type of output here. We can move back and forth. We can see we have 3 bash sessions here, actually. And which is what we do, because we have one window here and these 2 windows all within the same job. We can see these all belong to me. They're mostly all sleeping because I'm not doing very much work. htop is running, it's using 1% of a single CPU, 0.1% of all the memory on the system. We can see here that this system has 4 cores and most of its memory is available. We can type in F10. We can type in F10 to quit. The same sort of thing here. There's htop running in this one here. And this one's nice because you could scroll up and down and if we exit here, htop, you can see free. Oh, let's run it on the other one. Free. It shows you your total memory, the used memory on the system, how much is free, how much is shared, how much is used by swap. Free minus M gives you megabytes. Free minus G gives you gigabytes. So for file system in I/O, there's a lot of commands you could look at. df, lsof minus p. Not all of these will be available on every single machine you have access to. I think IOTop requires elevated privileges, for instance. But you can use quite a few of these. So df for the disk free, df minus h for human readable. LSOF. LSOF is not found here, but what LSOF is a list of open files. Here are on Beluga. I could actually pick that up. Here's all the open files that are used by everybody on the Beluga head node, Beluga 2, that are logged in. If your program starts opening and closing, or opens up, a million files, and that's the performance issue, LSOF will tell you. You could search for here if your program has many, many files open. Well, sometimes that kills stuff. LSOF minus P. You can, oh, no manual entry. Well, so it's available on Beluga, but there is no manual for it on Beluga. Well, just search man LSOF on Google. Google will tell you. And you should have the P flag. And here it says P is just list the open files by single process. So if you want to just see your own process in Beluga, or your single program, how many files it's open, well, you can run LSOF. Quota is another big one. This is my quota on Beluga. You can run quota here on the cluster, and well, some of our file systems don't like that. But this is a little play cluster we've created in order for you to be able to run jobs. What else can we show? dstat. dstat shows you some disk stats. These are the total disk stats for the system. There's disk total, network total. You could use htop. So in htop here, you could have htop show you a lot more stuff. So if you type in F2 and go to the columns, oh, and go to available columns here, there's a lot more available here. Oh, you could even do things like the children's process information, but where is disk? There should be disk here somewhere. Oh, here, IO rate. You can even have IO read rate or IO write rate, but let's just look at IO rate here. And we're done, so F10. So here now, htop is showing the amount of disk IO. Actually, if we do htop minus u user, because we want to concentrate on what we're doing, here we can see that our commands basically are not reading or writing very much. You can set it up so that you show the reading and writing separately, but we just have bash sessions that are basically sitting, not doing very much here. Any questions in this stuff? And by the way, htop saves the settings. So here we could see the disk is stuck here. In fact, let's go to the setup. Well, we can't see in a smaller window. Function F2. Look at the columns. Let's say we want the percent memory to be higher. We can set that up. Now we see CPU, percent memory, disk, PID, and so on. There's other information we can get. Uptime. Uptime is the command. It shows you how long the machine you've been running on has been on. In this case, 10 days, 46 hours, 4 hours, 36 minutes. We also see the load. How heavily is it loaded? We could type in who to see who's logged in. In this case, nobody. Well, nobody's logged in because we're accessing this machine via SLOC as opposed to SSH. Who am I? Gives you your username. But if we exit out here and I type in who, well, this is all of you guys on the login node. That's because I exited the job and went back to the login node. Here, I go back to the job. Other information, well, so the Unix system by default it keeps a lot of its data so Unix keeps track of a lot of its data and allows you to see it as if it were a file system. So if you look at the proc part of the file system, so we could do an ls and root. Here is the top of the file system. And then we look at proc. We could look at meminfo. It's a file, but it's not really a file. It's just the computer pretends it creates a file every time you look at it, and it actually gives you the information on the memory on the system. So Unix likes doing that. Everything is a file to Unix, including its state. It just writes the state to. It lets you read the state as if it was a file. Let's put it that way. So it tells you the total memory that's available here, total free memory, and so on. You could do the same thing about CPU state, proc CPU info. It tells you about the process, genuine Intel, processor 0. It's E3, Intel Xeon, Ivy Bridge. Tells you how fast it is, how much cache it has, that sort of thing. So there is another file system, sys, fs, CPU set, C group CPU set. So in this file system here, this is how Linux keeps, or Unix keeps you from stepping on other people. This is sort of a jail for each of our jobs that run on the system. So you may wonder, well, what happens if multiple people run on the computers and then they get jobs on the same machine, and then one person uses much more resources than they asked for, right? Well, what happens is actually Unix prevents that from happening. So via a process of a CPU set or a C group. So these are the slurred CPU sets. So yeah, that's mine. And that's job 81. And we're on step 0, I think. And we can actually see these IDs here. So these are basically all the processes that are running, actually. Which step am I in? Well, I'm in step 4. That makes sense. Oh. I want to go back here. Oh wait, I exited the job by accident. Okay, I have to go back in. I apologize for that. Right, I'm user 14. My step ID is 5, so if I echo $, it's my process's shell, my PID of my shell. You can actually find it in the tasks here. So this shows you that we are inside the jail created by the Unix system to stop your job from stepping, or from me from stepping outside my job and stepping on somebody else's job that's running. This is fairly advanced Unix though, so you don't have to know about this for the vast majority of you, but know that there is a mechanism here that prevents your job from stepping on somebody else or somebody else stepping on your job. Okay, we're halfway through our material here. Let's take a few minute break. If you have any questions, please feel free to ask them. So let's come back here at 2:21. How has it been so far? Is it too fast, too slow? Was there anything you guys were hoping I covered? Okay. So it's 221 again. Oh, again, it's 221. So we'll start again. So now we're going to actually go into the practical component. So actually, I'm going to exit out here. And we should be automatically logged out here. Yeah. So what you should do right now is we're going to want to go to the Etherpad here, grab this command here, wget, and we're going to want to download a program called Cryptic. We're going to want to change its mode. Okay. We're going to use this for later. Okay. We want to make it executable. Another part of the we're going to want to get ourselves a node with some more memory. So just run salloc minus mem 3900. Our nodes here have just slightly less than 4 gigabytes of RAM each. So this gives us, in our job, almost the total 4 gigabytes. So here I started job 83. So here I started job 83. I'm going to want to join this job. Let's run, oh, wrong window. In the other window, you want to join it. Let's run minus job ID equals 83 minus ppy bash. There we go. And now I'm in the same job on both. So you want to have 2 windows open, and you want to be in the second. You want to be in the job as well, in both windows. Now we'll run htop minus your user. And here you could see that there's basically only 2 versions of bash. Basically just bash running. So one from each window. So let's say we're trying to actually do some real work here. And we want to see how much resources our job is using. Well, we're going to do that. Now, if you were in HPC Essentials, you would know that Compute Kernel uses software modules. So if you do a module avail, you could see all the possible software that you can load and all the versions and so on. So what we're going to do is we want to load a few pieces of, well, let's go module avail octave. It doesn't find octave. There is a command called module spider that will actually show you more software. but there's some prerequisite modules that have to be swapped over. So there's a whole bunch of modules that will need to be loaded in order for us to load this octave. Well, let's start with that. Module load GCC. Module list. You can see most of those modules are already loaded. Now if we do module avail octave, we should see it. Module load octave. So now we've loaded Octave. What is Octave? Octave is basically a free version of MATLAB. So that's a pretty neat thing because we can use this machine interactively. Just like MATLAB, Octave can be run. There's a GUI to it as well, just like MATLAB. There's two different modes, the GUI lesson, with the graphical user interface mode and the command line mode. Because of this talk, I'm just doing everything in the command line, but we'll turn on Octave and do some calculations. And yeah, it's just like MATLAB, so, but a free version of MATLAB, basically. We could see here, we could see here that Octave is running, right? You can see basically it's using no compute, no memory. Okay. In Octave, it's linear algebra. Let's create a vector. Here we have a vector from 0 to 5 in 0.5 increments. We could create a vector B, which is basically some math on vector A to also have some numbers here. No. So B is equal to 2 times A squared plus 6A. So B1 is equal to basically 2 times the number in A1 squared plus 6 times A, and so on. Just some linear algebra. We can plot it. And here we get a somewhat ugly plot. But this is because we don't have X installed, so we only have a GUI, we only have the command line terminal to see. If you were doing this with X11, you would get a plot on the graphical what's it called, plot. Okay, so but we could see how many resources our program uses. So let's do something. Let's create a vector D that is 10 million digits long. In this case, if we do a slice of D, we can see that the first number is 0, the second number is 1, and so on. So we created a vector that is 10 million long, and we can actually see the memory that's used. So just by creating this vector, we've used 3% of the memory on this computer here. Okay. Let's create another vector, E, just like that, just like the previous vector. Oh, look, our memory has gone to 5%. Let's multiply every single number in E by every single number in D. So the first element of E by the first element of D, and put it into vector F. And run that. And what we should see here is we should see that the octave should use some computational time. And that's what we see. Boom, it went up for a while, and then it went down. Also, the memory increased. So here we can actually see that when we run something in MATLAB in real time and we use more memory or we use more compute, we can see it in the top output. So oftentimes people ask, well, how could I tell how much memory does my program use? Right? Because when you want to run a job, you have to tell how much memory for the system to reserve. But how do you know how much memory your program uses, especially if it's very large? Well, you can ask for more, run it in the job, attach to the job, just like we are right now, and run top while your program is running. And there you can see how much CPU percentage in CPU, how much percent memory it's using. So this is the way you figure out how much memory your program is using. Any questions? Okay, I'm going to demo something here on Beluga that is grabbing a GPU. So if you have a Compute Canada account, this is going to fail for me because I have more than one account, so I have to specify which account I need to use. But here in Compute Canada, boom. And I have to spell account correctly as well. And right here, I have a compute node with a GPU. This is a V100 GPU. These GPUs go for something like $10,000 each. Or at least did when somewhere around there anyway. But here you have access to it. I've asked for a GPU, one of the interactive GPUs. I've got it. I could run a job. If I wanted to get output and watch what's going on with the GPU, I could actually type in the watch command. Oh, there's a watch command. What it does is it runs the same command all the time. So I could type watch minus n1 every second, run hostname, and every second it's going to run the hostname command, which is just going to be answer the same one every single time. Control C to kill. But I could have a watch minus n1, and then something that I want to keep track of, like what's going on with the GPU. So if I had an extra window to run, if I was running my GPU job in one window, and in my other window, I could run NVIDIA SMI, and with the watch command, and you can see it's being updated all the time, and it's actually giving me information on the GPU that I have, like how much watts it's actually using right now, how much memory it has available and it's using, how much utilization do we have. So this is the way you would profile a GPU job running in a Compute Canada cluster. Right, you'd want another window to actually run your actual program inside this job that we have, right? Not just the profiling, because I'm just demoing the profiling here. And look how fast we got the resources. They're practically instantaneous. So if you want to do development, basically do an salloc, maybe ask for an hour or two, because this is going to kick me off after half an hour, which is the default of an SRLock. And I think the most you're allowed is 3 hours if you're going to run on one of the interactive nodes. So ask for 3 hours, get it, start running your GPU job, attach to the job with the other srun, run watch -n1 NVIDIA-SMI, and you'll get to see how loaded your GPU is all the time as well. Of course, you could have another window open with top. Control-C to kill that, exit to end. And notice that the jobs on Compute Canada Beluga cluster are a lot higher numbers. So it's, my job here was 12 million. Its ID was 12,204,111. Well, my last job on this Tesla cluster, what was it, 84? SAR perf, okay. So there's SAR and perf, which are more complex and advanced profiling tools you could use as well. You could use actual debuggers as well. So once you have interactive access to the shell, you could do debugging using the standard Unix debugging tools. So any questions on this? So I'm going to talk about SLAM jobs in memory. So you always need to ask for slightly less than the total memory on the node, as some of the memory is used by the operating system, and your job will not start until there's enough memory available. So you can't ask for all the memory on the node because some is used by the operating system. So it's a good practice to ask for memory in thousands of megabytes and not in gigabytes, because of course in gigabytes you have 10,024 megabytes in it. So if you ask for thousands of megabytes, there is a little bit of memory left over for the operating system to use and so on. And you may specify the maximum amount of memory available to your job in one of two ways. You could specify the total memory used by your jobs using mem equals, or you could specify the memory per core with mem per CPU equals in terms of megabytes. Now, it's important to specify the memory correctly. If you don't ask enough and your job uses more, your job will be killed. If you ask too much, it will take much longer time to schedule your jobs and you will be wasting resources. If you ask for more memory than is available on the cluster, your job will never run. The scheduling system will not stop you from submitting such a job or even warn you. So, sometimes the scheduling system is optimistic. Oh yeah, I've asked for 8 terabytes. Maybe, somebody will buy a node a server with that amount of RAM. And your job will sit in the queue waiting for that to happen. You probably don't want to wait to do that. So be very careful. Don't ask for absurd amounts of memory because you may be waiting forever. Also, if you don't specify any memory, your job will get a very small default maximum memory. I think it's 256 megabytes. How do you find out how much memory your job used? Well, you could look at top, htop, all those commands, looking at processes and so on. You could also use sstat and saccount -j job ID, and then ask for this information. Or just do the easiest way, log in, get into the job, and actually use the Unix commands. One thing that you may want to look at. So oftentimes in the Unix commands and so on, you will see max VM size and max RSS. So those both refer to memory, but they refer to different things. So a program can ask an operating system to use a chunk of memory. And once it asks the operating system, that's virtual or requested memory. So that is the field max VM size. But until your program actually uses the memory, the operating system won't necessarily allocate the memory to your program. So the actual memory that your program uses is called max RSS, or max resident set size. So when you're on top, or htop, you see virtual and res here. Virtual is the it's the memory that this program requested. Res is the actual memory the program is currently using at this very moment. Right, we're on htop. That's the same thing. Here you have virtual and resident, and resident set size. So currently, we have, okay, let's exit Octave here. So any questions up to this point? So we have one thing for you to do. So you have downloaded a program called Cryptic, right? You can download it right here with the wget. You can rerun it again, wget, and then chmod it, change its mode, make it executable. Now here, I'm already inside a job. Actually, let's do the whole thing. Oh, function 10, that's good. That's good. Okay. Here we are. We have, oh, I've downloaded it twice. Let's remove the extraneous copy. What we want to do is create a job for us, for ourselves. So you could find the information right here for a job. One node, one task, and we're going to run cryptic. So here we are. Can you run this cryptic program? So the idea here is you have a job. It's cryptic. So this program, we don't know how much memory it uses, how much resources it requires. We want you to try to run it. Now, you could try running it without asking for memory. That's probably going to fail because this program requires some memory. And I want you, in this example here, to run this program and figure out how much memory it requires. And in the meantime, does anybody have any questions?
Hey, Camille, I'll just make a comment. So your script snippet in the Etherpad, if you look at that, it says n tasks equals 1. It needs a minus minus in front of that n tasks. Same with the next line with the nodes. So if people are copy and pasting, they might run into trouble there.
Oh,
I'll just add the minus minuses.
thank you.
You're welcome.
Yeah. If your program fails because it doesn't have enough memory, you probably want to ask for some memory. This or memory per CPU. Probably want to put in some number there. I should use nano because that's what we're. Yeah. So if you got cryptic running and know how much memory it requires, give a green check mark. So does anybody know how much memory our program uses? Our cryptic program? Yes, we have an answer from somebody. 3,076 megabytes. Yeah, that's roughly what it uses. So let's go over how we would get there. So if we try running cryptic with just 1 gigabyte, immediately what we get is detected kill events. Kill is an out-of-memory killer. So if in step 99.batch cgroup, so basically what it means is there wasn't enough memory resources available there, and the operating system has killed your program which tried to use too much memory. So some of the processes have been killed by cgroup out-of-memory handler. So when you see something like this, well, you want to ask for some more memory in your job. Let's go in here. Now the maximum amount of memory we could ask for a job here is 3,900 megabytes. We're inside the job now. We run htop, and here htop sees that cryptic is using 3,076 megabytes of RAM. So in such a case, you'd probably want to ask a little bit more next time you run your job. Maybe you'd want to ask for 3,100 megabytes of RAM, maybe 3,200 megabytes of RAM to run this type of job. You know, slightly different input into your simulation may use slightly a little bit more RAM. But here we determined how much memory your program needs. Of course, you could look at other things like, you know, is your program doing too much I/O, input output? Is it writing too much to the disk? Or anything else like that. So we're now at the end of our lesson here. Does anybody have any questions? Any at all? Oh, how did we know that the memory required 3,076? Well, actually, we knew that because that's what it says so right here using htop, right? Because we went into the job and we were actually able to see how much memory the job was using, right? So I think we So here we've been kicked out because the job has finished. But if we rerun our job again, we're now in job 107. -7 minus pty bash. So join the job. Now we are inside job 107, right? Could print env grep minus I slurm grep minus I id. Grep minus I id. You can see we're in job 107. We do an htop minus u and ourselves. So here we can see all the programs that we're running, all the processes that we're running, including Cryptic. Here we can see Cryptic is using 77.8% of the memory on the system. We could see its process ID, that it belongs to me. Then we could see its resident set size, 3072. That's how much memory it's actually using, 3076. It's the memory the program asked the operating system for. So this is how come we know how much memory the program uses. We could also see how much memory is being used on the system, since we're the only ones running on this machine. But that just up here is the total memory on the machine. Does that answer your question, Debbie? Okay. Right, and we should be kicked out of here as well. It's going to kick me off in a few seconds. Because the job has finished, right? This is how we would test and find out if there's something else is wrong, right? This is how we'd look at the GPU statistics if we were running a GPU job. This is how we'd look at how many files we have open, if that's causing any issues. If we had network traffic, we could look at network traffic as well. So this is how we can profile, debug, and test our jobs, figure out how much resources that they use. Also, when we're inside a job, right, we do an salloc. If something crashes, well, the bash session is still running, right? So because of that, we can, what's it called? We can have programs fail and not have to wait another hour or two for resources to become available. So we could use it for development as well. Are there any other questions?
Well,
Yeah.
did you mention the ceph command at all?
Just only in passing.
I just mentioned that I got it working. It was broken, and
On the test cluster?
yeah, so that's sometimes a useful way to determine how much memory your job needs, for example.
Yeah. Yeah. So it's also possible for you to just ask the scheduler, right? How much memory your job used. You can also do it with the stat command and the saccount command. And the ceph when it's installed. But by far, SLOC is the most powerful idea, where you can jump into the job, because Unix has many, many tools. And they're quite nice ones, like HTOP. Any questions at all? You could ask me even questions about the other courses right now if you want. Well, thank you very much, everybody. If you have any questions, you can email us.
Thanks, Camille. Very informative talk. And we'll just give another minute or two. We'll give another minute or two, and then I'll end the meeting if no one has any questions.